All right, good morning. Um, we're about to get to the greatest theorem in the entire textbook. This is theorem 4.20, the single best theorem in the book. These are representative of the rules errors for the trapezoidal and Simpson's rules. Um, as you can see in the little paragraph underneath, it should be noted that these rules are used to determine what's referred to as an upper bound, which means the maximum possible error that could be achieved. And for the trapezoidal rule, you can see right here, that error is dictated by the maximum of the second derivative. And for the Simpson's rule, it is dictated by the maximum of the fourth derivative. What we're going to be doing is solving for n. In other words, we're going to be attempting to predict a value of n, which will have a very specific error. So what I'm going to do is let's look at our first example here. And to do this, we're going to look at some problems from the text. Okay, so you guys are tasked with doing the odds. So let's do an even. Let's do number 32. So number 32, here we go. It says, use the error formulas in theorem 4.20 to find n, such as the error in the approximation of the definite integral is less than or equal to 0.00001 using the trapezoidal rule and Simpson's rule. Now, what's important to note about this is we are given the error value right here, the e in this case, and asked to determine what the n will be. So this theorem works really well if you're given e and asked to find n. And it can also work the other way, but that's the less common usage, where you're given n and asked to find what the e value is. And so let's take a look at number 32. It says we have the integral from 1 to 3 square root of x on the denominator and dx. So for our function, we're going to determine what type of error we're going to have, given if we wanted to determine, for example, in this case, 0.123401. And we're going to do it with the first, the Simpson's rule, and then secondly, with the trapezoidal rule. Sorry, backwards. Okay, let's do it. So to do this, I'm going to first need to take a second derivative and determine its maximal value. So to do that, let's go ahead and take a look at the function 1 over the square root of x. And I'm going to take two derivatives. So let's first convert this into power form. So this will be x to negative 1/2 power. And then I'm going to take two derivatives. So the first derivative is negative 1/2 x to negative 3/2. And the second derivative so I multiply those two and get positive 3 over 4 x to the negative 5/2. So there's my function. This is my second derivative. Now, eventually, I'm going to need to take my fourth derivative if I'm going to do part B. So I'm going to go ahead and keep this in mind when I take my next step. Now, what I want to determine is the maximal value of this function in terms of x. And so what I want to do now is I can look at a graph of this function, which would be one great way to approach this problem. I could also just use some properties of the function since it's a negative power. But I need to find the maximal value on the range between 1 and 3. So let's go ahead and take a look. In this case, since this has a negative power, this is going to be a fractional function, which means that for this particular function, it will be decreasing in the entirety of its domain. And so if this is my function, this would be equivalent to 3 over 4 square root of x to the fifth. If I plug in 1, this function will have a value of 3/4. If I plug in 3, this function will have a value of the fifth power. That would be 243. The square root of 243 would be closer to 15. And then 3 divided by 4 times 15, 3 divided by 61 over 20. That gets much smaller. And so I predict that the maximal value of the second derivative is going to be 3/4. So again, I use some logic about how this function looks. I could also look at a graph of this function, but I want to make sure to define the graph in these parameters to try to find the maximal value. And so again, notice that I use the actual value itself, 3/4, not the 1 that gave me the 3/4. I use the 3/4, and then I plug into this function. So it says the error is less than or equal to b minus a cubed over 12 times n squared times the max of f double prime of x. So from here, I plug in my error, which is 0.00001 less than or equal to. My b value is 3. My a value is 1. I cube it. I have 12 n squared. Notice I want to find n, so I leave n in the problem, times the maximal value, which is 3/4. And now my goal is to solve for n in this function. So let's do this. I'm going to convert this into a decimal. Now, this would be tenths, hundredths, thousandths, 10,000ths, 100,000ths. This is equivalent to 1 over 100,000 less than or equal to 3 minus 1 would be 2. 2 to the third power would be 8. So we end up with 8 over 12n squared times 3 over 4. Okay, so in this case, the 8 and the 3 become a 24, which would cancel with everything except a 2. So we end up with 1 over 100,000 is less than or equal to 1 over 2n squared. So from here, I can flip these around, cross multiply, standard algebraic procedure, as long as n is positive. And then I would end up with 2n squared is less than or equal to 100,000. Divide everything by 2, I end up with n squared is less than or equal to 50,000. And then I can square root both sides and determine my solution for n. So my n must be less than or equal to, let's see, the square root of 500,000. Oh, Jesus. I'm going to pull out my calculator function on my computer. Let's see, 50,000. Plug in my square root is, oh my gosh, 223.6, which means that if I want to achieve that actual value, my n has to be 224. Because keep in mind, this is supposed to be a value that is obtainable n. So I can't just choose kind of a random n that's, a decimal. N has to be an actual value I can plug in, the number of rectangles. So 224 is my value. So if I want to get to within 100,000th, it would require me to use 224 rectangles using trapezoidal rule. For comparison, if I wanted to do this with the standard left and right hand rules, I'd be looking at somewhere close to 1,000. Now I'll do the problem again using the Simpson's rule instead. And what we're going to see is that the Simpson's rule is far more accurate. And so while it took 224 to get us this value from our function, doing it with Simpson's rule is much faster. So let's do it. So b. Now I've already got the second derivative. It is 3 over 4 x to the negative 5 halves. So what I'm going to do now is I'm going to take the third derivative. So I multiply, so we end up with negative 15 over 8 x to the negative 7 halves. And then I take a fourth derivative, which would give me positive over 16. 7 times that would give me 105. X to the negative 9 halves. Okay, that looks pretty good. And from here, what I do is I take my function. Now that I have my fourth derivative, I want to determine the maximal value. Now, to do this, I can either use my graph or I could use my properties, since again, this is a function which does in fact have 105 over 16 square root of x to the ninth. This function is a decreasing function over time, and so I can look at this function and know that it's going to get smaller over time, so I know 1 is the correct value. Or I can plug them in and see that if I plug in 1, I get 105 over 16. If I plug in 3, I get something that is significantly smaller. And so I'm going to use the singular value of 1, which would give me a value of 105 over 16. Again, which comes from the 1 value. I could also look at the graph of this and determine from the graph that this is in fact the highest value. Again, I want to look for the maximal of this fourth derivative. So I use the fourth derivative function, and I find its max value, and that's what I'm going to be plugging in. All right, so we know that the error, which is 0.00001, or 1/100,000th, is less than or equal to b minus a to the fifth over 180 and the fourth times the max of f the fourth derivative of x. And now I use my components, so 0.00001 is less than or equal to, my b value is 3, my a value is 1 to the fifth power over 180 n to the fourth times 105 over 16. From here, let's see what I can do to make this function a little nicer. So this is again 1 over 100,000. And from there, I take my function. 3 minus 1 would be 2. 2 to the fifth would be 32. Over 180 n to the fourth times 105 over 16. Now the 32 and the 16 are going to cancel, leaving a 2 behind. The 2 and the 180 are going to cancel, leaving a 90 behind. The 90 and the 105 are going to cancel because they're multiples of 15. Let's see, if I take 15 out of this one, I would be left with 7. 15 out of the other one, I would be left with a 6. So I end up with 7 over 6, or the function 1 over 100,000 is less than or equal to 7 over 6n to the fourth. From there, I cross multiply again, just like I did in the previous problem, to end up with 700,000 is less than or equal to 6n to the fourth. I divide by 6 and take the fourth root. When I divide by 6, I get n to the fourth is less than or equal to 700,000 over 6. I'm not going to bother simplifying because I'm immediately going to pull out a calculator and take a fourth root. And that should be my function. So I end up with n is less than or equal to, again, calculator is very beneficial here. So I take my function. This one will not do that. Okay, I'm going to pull up Google instead. Google says my function, let's see, 700,000 divided by 6. Just the 1/4 power. So the number I get this time is 18.48, which means my n value would be 19. So this is the small difference that exists between the trapezoidal and Simpson's rules. So you got to remember, you got to think 1,000 is how many it would take by the traditional methods. With this trapezoidal rule, it takes 224, and with the Simpson's rule, it only takes 19. So by comparison, the Simpson's rule, if I don't have a function that it can easily integrate, this can allow me to take that function and find its value very easily with only 19, as opposed to in the hundreds or in the thousands. And so this is the advantage of something like the trapezoidal rule. And again, it's done by derivatives, which are much easier to use, and many more functions have derivatives than they have integrals of. And so this was problem number 32. Note a couple of the big parts of it that are really beneficial here. So to get this to work, the best thing you can use is this component where you have the function's formula. Then we take that function, we take multiple derivatives. We then have to find the maximal value, which is found by looking at either a graph or by using algebraic rules. With that value, we then can plug into our error formula, and then the last step is to solve for n algebraically. And once we have n by itself, make sure we want the highest or next highest value of n that works. So if it's just a decimal, like 223.6, we have to go to 224, because it's the n that will give us this error has to be bigger than that. Because if it's smaller than that, it won't give us that error. And the same thing for the Simpson's rule, but in this case you need a fourth derivative. And so don't double up on the work. Use the work from part A to help you solve part B and be able to find that solution a little bit faster and easier. So there we have it. That's all the lesson for today. I'll be posting a video here, and I hope to see you guys tomorrow if there's no ice in the road. So I'll see you guys then.